Will new processor architecture raise energy efficiency? Data centers continue to heat up as a new processor consume more energy than ever before. Cooling is the primary weapon against the heat these processors generate, but it won't be able to keep up forever with the traditional processor architectures. New ones may be necessary. These opportunities today to make well-known architecture more efficient, energy efficient, but the number of the options for substantial changes is dwindling. As a result, new architectural ideas are being considered with some moving to commercial availability. Some are very different from what exists today, even to the point of trying to recycle energy within circuits. But processors don't exist in a vacuum. They have broader ecosystems, including support for operating systems, coding, compilation, testing, and debugging. Would any architectural changes to be compelling enough to force a large-scale infrastructure change? Is the era of the general computing over? Embedded processors have long been tuned for specific applications. In the past, people chose off-the-shelf TSP CPUs and used them as is, but the expense of the power consumption, said Prakasi Madhuvatasi, is a product marketing director for Tensilica Audio Voice DSP at Cadence. Data centers and PCs have employed general-purpose processors because the workload can incredibly varied. But the trade-offs made for generally may be too much of the impediment to power reduction even in the data center. The history of the system on a chip has been one of the progressively more specialized, said Steve Lobby, chief marketing officer of Quadric. The SS era began with the first such chips having only one programmable processor on chip, a CPU. Over the years, each new major category of the processor core has been additive. A new type of processor added in addition to the CPU or CPUs. The creation of each new category has been a reaction to growing demand for a specific class of compute revolving around the data types and computational intensity that CPU are not well suited for address. Lodi noted there is a style of computing that CPUs do particularly well, and a style that benefits from GPUs. CPUs are designed to chase pointers in C code, he said. They are not efficient at a highly repetitive task of drawing polygons, no matter how far you try to stretch performance with customizations. Second generation MPUs with the support for more AI graph operator instruction quickly replaced the first generation. But a CPU with a heavy accelerator is still just like a pointer chaser wielding a set of crutches with a roller stake. He continued. In 2025, we see the emergence of the full C++ programmable neural processing unit (NPUs) in SoC designs that completely shift the AI workload of the legacy CPU and onto a purpose-built processor tailored to the task. Tuning such as architecture requires extensive workload profiling. When you run workload data represent your final use cases, you have to make sure that the choices you make for instructions are tuned to your application, said Mathvapati. You balanced the areas increase that each instruction provided with the performance benefit it gives the power consumption that entail. When you add area, you also increase the dynamic power a little bit, and you also increase the static power because static power is proportional to the area. This also is happening in the data center. Instead of replicating a single general purpose architecture throughout, different grouping will be summoned for different workloads. This is already the case for AI, but it may go beyond that, allocating servers according to the needs of the workload. Data flow processors as an alternative. One way to approach this to look into how data flow through the processor. For example, efficiency computer claims its data flow architecture can reduce the general purpose computing powered by the huge amount. We are getting compared to the other parts in the marketing doing embedded computing, and we are seeing 10 times to 100 times improvement in the energy consumption compared to those other offerings, said Brandon Lucia, CEO and co-founders of Efficient Computer. Efficient architecture uses the area of the computing tiles that have instruction fetching. No cycle-to-cycle configuration of the sort. A standard processor must perform an instruction change, and no indirect data movement. Instead, the compiler statically assigns the instruction to specific tiles. After loading, those instructions remain with the tile. Figure 1. Efficient data flow processors top as compared with the typical one on bottom. Most of blocks in the additional processor go away with the efficient architecture, or as do some of the standard elements in the design and the main computing titles. Source: efficient computers. The network on chip NRC connects the tiles, but unlike a typical NRCs, this one has circuit switches like old phone systems, not packet switched. When the network is configured, data simply flows with while connection remains open. The energy efficiency on chip network allows one of the tiles to talk to any of the other tiles. At configuration time, so you set up a tile to execute the instruction, and then you set up the routes between these tiles, and so that when an operation runs on a tile, it produces an output that gets routed directly to the input port of the downstream instruction, Lucia said. This is very simple in concept, but not entirely novel. Deeply embedded code has limited workloads and always does the same thing, but making it a more general purpose requires some enhancement. Loading on the fly. It might seem that this approach would work only for programs that can fit onto the area in their entirety. So the first production configures is a 12 by 12 array. So that's not a lot of tiles. The company is working on larger devices, and the tiles can scale, and the efficiencies also must scale the memory and I/O subsystems, which requires more work. So at least for the time being, this is the huge array of cores. To avoiding limiting the program size, the company has included a reconfiguration capability that can swap and code. It's like continuation passing, explained Lucia. We reconfigure in a pipelined way so that as the first continuation is finishing, the second one is getting configured onto the fabric and can begin learning as soon as inputs are available from the previous continuation. They employ a distributed Downes algorithm to determine when to reconfigure. Reconfiguration is partial, that any tile that's completed that can be reconfigured. However, arbitrary partial reconfiguration in the absence of a down signal isn't possible. Execution is nominally asynchronous in that a tile begins computing when inputs are ready according to the ready valid protocol. Explicit scheduling isn't necessary. That simple protocol allows us to do unicast, multicast, and broadcast the communication from one tile to any other tile very efficiently without the need for synchronization or centralized data structures. Explained Lucia. You distribute the responsibility of synchronization between the tiles, and it simplifies the design considerably. The other big requirement for general computing is the ability to handle conditional execution. That means branching, but it also affects loops which must test against the iteration limit to determine. When they are done, the simple answer is convert everything into steering operation. Based on the input signal, a decider, the output is on one or the other path. By using up an entire tile only for such a basic operation would be inefficient. Instead, it turns out that each tile can fuse instruction, so conditioner can be fused with other instruction. On a given tile, you might have 3 or 4 or 5 operations encoding and the configuration of the tile as they are fused together, explained Lucia. As with the function units in the conventional course, different tiles have different capabilities. Some of them can do things like multiplication, some of them can do things like 32-bit floating points, and other ones can't, said Lucia. Code profiling during chip development determined which tiles received which instruction. The number of the fusible instruction dependent on the tile and the resources the remaining the tile out fuse instruction claim them. Such an architecture can exploit parallelism as long as the compiler can detect it. The company says no special programming techniques are necessary and the standard code will work. Unlike accelerator, we able to do these general purpose things even for really freaky code, said Lucia, who said an old copy of the Doom program ran successfully. The energy recycling, and even more revolutionary approach to processing comes from Valley Computing. Its underlying philosophy is based on thermodynamics. In CMOS, we represent bits using voltage levels on circuit mode, and there is some signal energy associated with those voltages, explained Mike Frank, staff scientist and Valley Computing. When we transit to a new voltage level, we dispatch the entire signal energy that we use to encoding a bit. That's because of the way the switching is done conventionally by connecting circuit nodes to constant voltage sources. Anytime you throw away digital information, you have to throw away the energy that is used to represent that information. When you are throwing any away information, you're just converting it to entropy, and the energy associated with the information is converted into heat. Wire has developed that it's called reversal computing. After performing an operation, that operation can be reversed to recapture much of the energy used. In reversible computing, we try to avoid throw away information, said Frank. Instead, we transform information in reversible ways no information is greatly getting lost. This enables you to recycle the energy that was used to represent those bits. The chip employs a redundant power supply, which adds the analog element to each computing node has computing, akin to the LC tank, from it pulls energy. Then it returns most of the energy. Inductors on chip. The company said losses can be made arbitrarily small and are typically associated with the leakage and the Q factor of the lithium. Each AC supply less than a DC supply, said Frank. Instead of the flowing from the power up supply to the circuit and then turning into heat, we push energy into the circuit to change its state, and we pull energy out of the circuit to change its state again. The overall architecture remains digital, but slew rates are managed to be slower, allowing the very adiabatic that is involving no gain or loss of the heat switching. It's still fundamentally a digital computer paradigm, and it has the reliability of digital, said Frank. It's possible to complete a reverse subset of the instructions to recover immediate states, although that's not the company goal. It wants to allow standard programming techniques which don't involve reversing, but it may be possible to further optimize the program by taking advantage of this. The slower clocking more parallelism. Clock rates won't be as fast as typical CPU clocks today. They will be closer to GPU clock rates. GPU clock speeds are much lower, so we are not that far behind compared to the GPUs, said Rodolfo Rossini, CEO of Very Computing. That's partly because the energy recapture takes time, adding to the clock cycle to its cycle, so it all happens within a cycle. Within the clock cycle, parts of the circuit are going forward, parts are going backward, decomputing things, said Frank. The overhead cut the clock speed by around 50%. This technique works really well when you have ridiculously massive parallelism, and fortunately, today's large language models are of that nature, said Frank. This can make up for some of the performance loss. One way be able to save yet more power by slowing the clock and doing in parallel. Well, the whole body of research around this topic, much of it's relatively esoteric, leveraging so-called Toffoli gates and ancilla bits. Wire appeared to the first to attempt a commercial offering. That means coming with the practical, usable, and affordable implementation of what otherwise has been abstract notions, including ones that don't involve the literal Toffoli gates, which are the economically inefficient. There are certain rules you have to follow, like not turning on a transistor when there is a voltage drop across it and not turning off a transistor when the current through it, said Frank. It turns out that if you obey those rules, it's logically reversible and it's highly efficient. It's not just a matter of carefully sequencing the transitions in a circuit and arranging the circuit topology in such a way that you perform a certain series of transitions on the driving signals that are controlling that circuit. And if you do everything in a right sequence, everything reversible and fully adiabatic. Still, Wire is a couple years away from the commercial availability, so architecture and the circuit details are not available. So, can we, architecture, succeed? Despite all the revolutionary challenges the semiconductor industry has brought to the world, it remains uncomfortable with the revolutionary new ideas. It's more comfortable with the revolutionary changes, which is why tweaks to existing architectures are always preferred. It takes a compelling problem and an equally compelling solution to drive more substantial change. Processors require an enormous range of tools, many of which come from third parties, so even though the software has been an Achilles heel of new AI architectures. A representative big developer must have for a new processor architecture to achieve mainstream commercial transaction. What we currently see as a big problem for new architectures is that you also need a big bundle of software stuff on top of it, and then the make it is so expensive. Said Andy Heineck, group leaders for advanced system integration and department head of the efficiency electronics at a Fraunhofer TÜV IIS, engineering of the adaptive system division. A good hardware solution is maybe 20% or 30% of what you need in total. This is often something we see with the startup. They ignore the software part, and it's clear to us they don't have any chance in the market. If a company such as Efficient Computer and Viral Computing can develop their necessary tools and work with an ecosystem to ensure support, they could have a chance, particularly if software developers don't really need to understand the underlying architecture programming. Both companies are trying to make their chips programmable using standard coding techniques. It ultimately boils down to an economic question. If we have enough pressure from the data center side that the energy consumption is too high, then we will see new architectures because it may also make economic sense, said Heineck. Success depends on the number of the factors, though there are no shortage of the new architecture being proposed that are purpose-built to focus on improving the performance, cost, and power efficiency, or for specific applications, said Stephen Wu, fellow the distinguished inventor at Rambus. Some subsystems are used for rapid development of the differentiated architectures like CPUs and GPUs. But for some critical subsystem like memory, a key challenge is finding the volumes necessary to enable new architectures due to the high development cost. Market must be large and offering a good return on investment, often leading to a chicken and egg dilemma of how to delay the new market is critical technology when the technology needed to do so hasn't been implemented yet. From a pure technology standpoint, big energy savings are possible. It's just not clear yet how to practical making happens, or if the processor designers must be satisfied with more measured approach that still help reduce power, but less dramatically. Okay, I read this article. Will new processor architectures raise energy efficiency? Thank you for your time. See you next time.